Hi, how are you?
Good. How's your holiday?
My holiday was good. It was nice to sleep in for a few days.
Same.
Okay. Just some administrative stuff while we'll give other people a chance to trickle in if they're going to. This is our last week of material, So today I'm going to finish up chapter 3 is about integration. These are the notes that we took last time on how we take the integral, and some of the rules. I'll go over that in just a minute to remind ourselves of stuff. So I'll finish up 3.2 today, and then I'm gonna do a big long example where we kind of bring things together, and then I'll do some problems from our classwork page, which is like integration using the power rule. Let's see, when you guys do the classwork for 3.2, you just need to do a handful of problems. Please don't go hog wild and do all of them. That's, it's kind of overkill. You don't really need to do that, but just pick and choose some of the problems that you want to work on. I'll go through a sample of the problems. So it'd be 3.2 classwork. Wednesday and Thursday, we will do chapter 3.3, okay? But this is our last week of actual lecture material. So what's going to happen next week is this. On Monday, we have 2 quizzes. We have quizzes for chapter 3.2 and 3.3. In the past, when we are in person, I just basically give the quizzes out at the same time, and it takes the whole class period. Because one quiz is a half class period, the other quiz is the other half of the class period. So you just get one whole class period to do both quizzes. We can decide, I can make those available during our class time, and we can decide on Monday that we're not actually going to meet as a class because we're just taking the quizzes. And I will post those quizzes on our Canvas page on Monday morning so that they'll be open when our class period starts. So that instead of logging in for class, you could log in and take your quizzes during that class time. I'll basically give you, essentially for the 2 quizzes, I'll give you an hour for a half hour for one, plus 15 minutes to upload it, and a half hour for the other, plus 15 minutes to upload it. Okay, so you basically get an hour and a half to do both quizzes, take pictures, and upload them to the Canvas page. So kind of be thinking about that. That's Monday, chapter 3.2 and 3.3 quizzes, 2 quizzes. The last 2 quizzes of the semester. And then on Wednesday, all sorts of things are due. So remember, this is a week now, not this Wednesday, but next Wednesday. All sorts of things are due. So on Monday, I'll be taking the rest of the homeworks, right? So Monday, I'll take the homework for chapter 3.2 and 3.3, and then I'll take the classwork for those chapters as well. On Wednesday, I'll take your problem sets. Remember, problem set 3 is on Wednesday, and then excuse me, also our projects are due on Wednesday. In the past, I've liked students to talk about their projects to the class, to discuss what they're doing, and we can maybe do that. I can look into how we share screens if you guys want to be able to talk about your project to the class. And I know we're not here on a whiteboard or anything like that, but if you wanted to, I can set it up so that I will share the screen so everybody can see you and hear you talk, and then you can talk about what your project was about and what you did and what kinds of algorithms. So maybe it won't be as detailed a presentation as I've done in the past, but don't forget your project report is due. And then also as part of the project report, when you do your methods and your results, right, your methods are all about the different equations and the algorithms that you're going to do. And the results are you working through the math of a couple of examples. So for example, if you've got something that bounces off a screen, you're going to say, I start here, and it hits, you do all the calculations for it hitting at this spot, and then the calculations for reflecting. And then it's going to hit this spot, and then it's going to reflect. So I need to see at least 2 iterations of, something. When you guys write up the math for that, you don't have to type that up. I know I've done enough equation writers that on the word processing stuff that typing, math in can be really tedious. So what I will allow for the results section is for you to write it up by hand. Hopefully really make it nice and neat so I can read it, okay, and nicely presented by hand. And you can just scan that in and submit that with like a PDF of your report. That'll go into your results section, okay. Remember, coding this up is not required. That is extra credit, okay. So please do all of the math first. Do those 2 examples first. Because that's what you need as to get full credit for your project. Okay, remember I gave you that whole checklist of what's going to be expected in terms of the project write-up. Okay, and then if you wanted to code things up, you know, do that only if you have time at the end. Okay, so kind of be thinking about that. If you want to talk about more about project stuff, we can talk about it in office hours. I'll be happy to go over it at that point. Okay. All right. So let's talk about where we were a week ago on Monday. So on Monday, a week ago, we started talking about chapter 3.2, which is essentially we're talking about antiderivatives, which means we're taking the integral of a function. Okay, you want to be thinking about g of t is a derivative of some other function, right? G of t is the derivative of f of t. So when I take this integral, I get the antiderivative, which gives me what my a possible original solution. Okay, so we had some rules for how we can take the integral to get the antiderivative. The first rule that we talked about was what was called the power rule, which is when I have an exponent x to some value, x cubed, x to the 1/2, whatever. And this all works as long as my exponent is not equal to -1. That's a separate condition. My power rule says I increase my exponent by 1 and I divide by my new exponent. I have to do plus c if I don't have any bounds on my integral here. Okay, my second rule is what do I do when the exponent's equal to -1? It looks like this. I'm integrating 1 over x, or x to the -1. When I do that, I get the natural log of the absolute value of that function plus c. Sine of x gives me minus the cosine. This a is some constant, right? It's like 3 or pi or whatever. And then I've got 1 over that value. This is my chain rule, right? This is my chain rule, but applied to integration. So 1 over a. Now minus, so sine gives me minus cosine. Cosine gives me positive sine, so it's opposite when we do our derivatives. Don't forget the 1 over a. And then still in the argument, I've got the ax. My exponentials, e to the ax gives me 1 over a, e to the x. This 1 over a again is from our chain rule. And then if I just integrate a constant, like I want to integrate 3, right? So I'm just going to get 3 times x, that whatever that constant was, plus I call this g or c1. This is a different constant. Okay. All right. So we're going to be applying those rules, okay, when we do this mega example here. So example 2, this is why I wanted to wait, because this example 2 is a really long, complicated, but it's a neat example because it pulls together a lot of stuff that we're talking about. So, and I just want to also point out, I think that there's a typo in our there's a typo in our notes. Like if you look at the lecture notes for this, there's a typo for it. So make sure that you're looking at the examples, and I'll post these lecture examples up on our class, our Canvas page a little bit later today. All right, so let's go ahead and start working through this. So we've got a particle. We're going to draw out a picture so you can see what this looks like. But we've got a particle, and it's initially at some position, and it's released into a well, and the well is shaped like a minus cosine. And it's given by this equation here. We're going to draw all this stuff out. So let's go ahead and actually do that while we're thinking about it. So our particle is at -1, +3. So this is our start. So let's write a little note. So this is, all right, this is my initial position, right? -1, -3. And it's just dropped. We're dropping it like that, okay? And it's into a cosine well. So our function minus the cosine of x. Let me just remember my cosine function. So my cosine function, 2 pi minus pi. Now here's pi over 2 there. So here's 1 minus 1. So my cosine starts off positive, positive, negative, here. So it goes like this, and then here's minus pi over 2. So it goes like this, right? And it goes on and on forever. It just keeps repeating. So this is my y-axis. This is my x-axis. So this is my regular cosine function, cosine of x, right? So if I do a negative cosine, my negative cosine basically takes all these values and makes them negative. So positive 1 becomes negative 1, 0 stay the same, but basically just reflects this. So it kind of looks like this, like that. Right, so this is minus the cosine of x right here. Okay, so that's the graph that we're looking at here. So now, right, it says we're looking at minus the cosine of x, and it goes from minus pi over 2 to pi over 2. Just roughly speaking, pi over 2, pi is 3.14. 3 divided by 2 is 1.5. So if this is 1, 1.5 is like right here, 1.5 is right there. So I'm going to use this roughly as my pi over 2 and negative pi over 2. So this is pi over 2 minus pi over 2. So my function says it's 0 everywhere, except it's on my cosine. So then this is going to be a minus 1. Right, so we're going to go like this. Right, so we're looking at a well like that. It's not drawn to scale. Look, my graph's a little off. Bear with me here. Here's our x-axis, here's our y. So our particle gets dropped into this well. So what's going to happen? Our particle gets dropped, and it's going to go boink, it's going to hit the well here, and then it's going to reflect, right? And so what we want to know is, given that the gravity in the world that we're in right here where this well is, the gravity is equal to 2, right? The gravity in our world is equal to roughly 10, right? 9.8. But the gravity here is equal to 2. So the gravity is a lot less. So when it comes in, what's it going to do? It's going to bounce, but the gravity, is it going to be able to make it outside the well or not? So we're going to use the gravity, okay? And we're going to use our position. We're going to use our shape to figure out when this bounces, does it bounce outside the well or does it bounce inside? Like, is it going to hit inside the well or is it going to hit outside the well? So we want to know that, right? Because in a game, you're going to have stuff like this where you've got some kind of like a sand trap or whatever, something going on. Your character's going to jump in and they're going to bounce, right? Given the gravity of the world that you're in, right? Is that character going to get stuck in the well? They're going to lose points and lose a turn, or are they going to be able to escape? Okay, so that's basically what's happening. All right, so let's think about what we need. We have a whole bunch of stuff that we're going to do. So we've got our velocity, acceleration, and position, right? Because we've got gravity that we're dealing with and our initial position. And we have things like reflections, okay, that we have to take into account. So reflections require tangents to the curve, they require projections and all that kind of stuff. So this is kind of like bringing together a lot of different things. All right, so let's start taking notes. Acceleration due to gravity. So I'm going to say my acceleration, and now I'm in a two-dimensional world here, even though reality is two-dimensional, but I'm going to look. So just minus 1, 3, that tells me I'm in a two-dimensional world. So my gravity is 0, minus 2. Gravity pulls us down. So even though they tell us it's positive 2, we know in reality that's a negative 2 because it's pulling us down. So that's acceleration. So I'm going to put a box around that. So to get my velocity, I have to integrate my acceleration. Okay, what that's going to do is I'm going to integrate 0 minus 2 dt, which looks like I integrate each bit and then minus 2 dt. Okay, this is a 0. Okay, to get my velocity, because the velocity is a vector. So now, and I'm going to say, so when I integrate that, I'm going to say when I integrate 0, remember, I'm going to get 0 plus a constant term. So I'm going to call it C1. And when I integrate a constant term, I get minus 2, that constant term, times t plus another constant, 2t, C2. Okay, so this is my v of t. Now I need to solve for C1 and C2. So my initial velocity at time t equals 0. So this would be v of 0. They didn't tell us anything. It looks like it's held and then it's dropped. So my initial velocity is 0, right? So that 0, 0, I'm going to use to help me solve for C1 and C2. So that goes C1 minus 2t plus C2. Okay, so this, I'm going to set each one equal to the other one. So this part here equal to C1, so 0 equals C1. And then 0 equals minus 2 times 0, because it all happens at time t equals 0 plus C2. So C1 equals 0, C2 equals 0. Okay, and this gives us an equation for our velocity, which is 0 minus 2t. Okay. All right. So why do I care, right? Because velocity is going to tell me my position, right? So this is dropping in, boop, 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 it's going at a certain velocity, right? It's going to drop. And what's my position? So I need to calculate that. So position. So x of t is equal to the integral of my velocity, which is equal to the integral of 0 minus 2t dt, which is equal to, right, we're going to go 0 dt, and then integral of minus 2t dt. Because it's a vector, so we integrate each piece. So I'm going to integrate that, and I'm going to get, this is, right, 0, I'm going to call it C1 again, because I get 0 plus C1, and then comma, I'm going to get, if I integrate, let's do this offline. So if I integrate a minus 2 dt, 2t, that's going to be minus 2 times t squared over 2, which is equal to minus t squared. Okay, and then there's a plus, another constant term. All right, so that's going to become minus t squared plus c2. And this is x of t. Now I need to solve for c1 and c2. Okay, so to solve for c1 and c2, I have to use my initial position. So when t equals 0, my initial position was minus 1, 3. X of 0 equals minus 1, 3. So I can set that equal to here. So I'm going to go c1 minus t squared plus c2. So this t here is going to turn into 0. So let's set each one equal to my x to my x. So minus 1 equals c1. 3 equals minus 0 squared plus c2. So c1 equals minus 1, c2 equals 3. So I'm going to plug that back in to get an equation for my position. Right, so my position C1 minus 1 minus t squared plus 3. Yeah, that gives me an equation for my position. Whew. All right. You guys with me so far? So we used our gravity to figure out velocity, to figure out our position. We needed a function to describe our position, given that we dropped it from this spot. Okay, so now let's think about what happens. Give you guys a minute to finish writing that. You all set? Okay. So let's think about what's happening. Remember, we're talking about when the particle hits the wall. So I need to figure out the time when the particle hits the wall. Right, so I need to solve for t. Okay, that's my big question. And I need to know what that time is so I can figure out a bunch of other stuff. So it's going to hit the wall when the y coordinate of our x of t is equal to our function at x equals -1. Why am I doing x equals -1? Well, x equals -1, remember, right here, we were told we're at -1, our initial position. So I'm like here, I'm dropping right down. So I need to say, I'm going to go, this is y equals minus the cosine of x. So when x is equal to -1, right, whoop, I plug that in, I'm going to get the y value, right? That gives you my function value. So what is my y position? I need to line up both of those y positions. Okay, and you should know that this -1 is in radians. We often work in degrees in this class, but make sure when you do this, your calculator is set to radians. Okay, all right, so now I'm going to plug this in. So this becomes y equals minus the cosine of x. So y equals minus the cosine of -1. Okay, so this is the function that we're talking about from the beginning. This is our well. Okay, so let's plug this in. So I'm going to set both, set the parametric equation for y equal to function equation for y. Okay, this is our well. Okay, so what that means, right? So our parametrics, write down our parametrics, our position. So our position function is given by -1 minus t squared plus 3. Right, this tells us the position of the particle. I want to know when the position of the particle intersects the position of the well, right? So when does the particle intersect the well? So I set this equal to minus the cosine of x. And this is at x equals -1. This is where particle was dropped. It was just dropped straight down, so I only have to worry about that. Okay, so x equals -1. So plug that in, minus t squared plus 3 equals minus the cosine of -1. And this is in radians, don't forget. So you have to check your mode on your calculator. All right, so when I plug in -1 multiplied by negative, what I'm going to get is minus t squared plus 3 equals minus 0.54. I'm going to solve for t, so I have to subtract 3 from both sides. So minus t squared equals minus 3.54. I'm going to divide by -1, right? So I'm going to get t, oops, sorry, you can't see what I'm doing. T squared equals positive 3.54. Then I take the square root, and I get t equals 1.88. Technically, there's a positive and a negative, right? Because I'm taking the square root, but I only want the positive time because we're moving forward in time, right? So t equals 1.88. So this represents the time when particle hits the well. Okay, so we solve for t, right? Once we find the time when it happens, I can use that time to figure out the position. Okay, so I can use this time to figure out the position of impact. Where does the particle hit the well? Right? So I take my x of t. Remember, x of t equals -1 minus t squared plus 3. And I plug in t equals that. So this is going to become x of 1.88. That doesn't change on my x. So -1 minus 1.88 squared plus 3. So my position of impact is -1 minus 0.54. Okay, so that's when it first hits. So let's just gonna look over back on my graph. Right, so it comes down here. So this is roughly, I didn't draw this very well to scale, but this right here, it's -1 because we're dropping it straight down. This here on my y-axis is -0.54. Okay, so this gives us the position of impact. Okay, We found the time when it happened. We used the time to figure out the position. That's good. All right, now we've got that. It's going to bounce, right? So now we're going to do the bouncing. Bouncing, reflecting. Reflecting is our mathematical term for bouncing. Okay, I'll let you guys finish writing that, and then we'll do the reflection part. Also upload the video later so you can see that you want to pause it. All right. So we're going to say particle. Which means it reflects. So that's the process that we're doing, the reflection part. Okay, so we have to figure out, so we need a bunch of stuff in order to figure out how we're going to make it reflect, right? So what we need is, let's do this, I'll draw it in purple. So in order to do the reflection, so it's going to hit right here, right? So I need my tangent line. So some tangent to the curve, which is our derivative of our cosine function. Because I'm going to use that tangent line, I'm going to use that to find the perpendicular. This is the normal. Normal to that, and I'm going to use that normal to help me reflect. Remember, we project onto the normal and we, subtract that. All right, so let's go ahead. So we need to get tangent to our curve, which is our well, right? We need the slope of our curve, which is our well, at that point at x equals -1. Why am I doing it at x equals -1? Because that's where it hits, at x equals -1. So that's the point at which I want that tangent to that curve, okay? So if my y, my function, is minus the cosine of x, my dy dx is going to be the slope of our curve, which is our well, and we're going to evaluate that at x equals -1. So I take the derivative of minus the cosine. Cosine derivative is equal to minus the sine. Minus times minus is going to give me positive sine of x. So I need to do this evaluate that at x equals -1. Remember, this is in radians now, so sine of -1, I'll write that again. So this is in radians. And why are we doing it at -1? Because this is the x coordinate of our impact site, right? Remember, we dropped it straight down. So when x is equal to -1, it hits the well. So that's our impact. That's where it's going to reflect. So I need to know what the slope is at that point right there. So sine of -1 in radians is going to give us minus 0.84. Okay, so that gives us a slope. All right, so let's write out things. So we've got a vector parallel to tangent line. Remember, this means that it's on our tangent line, right? And that's going to equal to, it's it's +1 in the x direction, not -1. Oh, that was my mistake. I don't have my white out here. So it's 1. And why is it 1? It's because this is dx. So it's 1 unit in the x direction and my slope in the y. This is 1 unit, and then dy dx. So it's always 1 because it's 1. And so this is, I made a mistake when I wrote negative. It has nothing to do with this right here. Okay, this just means I'm going 1 unit in the x direction, and that's equal to 1 minus 0.84. So it's a vector that's on my tangent line. What did I say we needed? We needed a vector that was perpendicular to that. Right? This example combines everything we've done so far. So we need to get vector perpendicular to tangent line Remember how we do that. We take the x and the y, we swap them, and we negate the new y. Minus 0.84 minus 1, right? So I switch the x and the y, so I get minus 0.84 positive 1, and then I negate the new y, so I get a negative 1. You know, we would like everything to be positive. We get the same answer. It's just prettier to work with positive. Make all positive numbers. And we can do that because all this means negative 0.84, negative 1 means it was headed this direction. Okay, but we want that direction because it'll just makes it easier. So we're going to make everything positive, 0.84, 1. Okay, so that's a vector that's perpendicular to my tangent line. I'm going to use that to help me do the projections and the reflections. Okay, so we're going to do that. Okay, so now do our reflection. Okay, so this is a reflection part. So all of that was like set up. We needed the intersection point when the particle was dropped where it hit the wall. What was that intersection spot? What was that point? To do the reflection, I needed the tangent line. I needed the perpendicular to the tangent line so I could do the projection and the reflection. All right, so I have to do the projection. Projection of V onto U. Remember that's going to be V dot U over U dot U times U. So this gives us a scalar multiple of the thing that we're projecting onto. So this right here, I'll call this my U, okay? And the thing that I'm projecting onto it is my velocity, okay? So V equals our velocity vector. Okay, so our velocity vector, let's see. Okay, yeah, I forgot to do that. All right, so let's do this offline here. So I'm going to do my velocity vector. So velocity at position of impact. Okay, velocity at position of impact. So that means I've got my x as 1.88, right? I'm going to go -1 to -0.54. Okay, that gives me that. So when we hit, my velocity at my time when we hit, right, is going to equal to, remember our velocity equation. Let's go back. Our velocity equation, 0 minus 2 times t. So I'm going to plug that in 0, and that's going to be -2 times 1.88. So my velocity is 0 minus 3.76. So there's my velocity vector, okay, as it's hitting. Okay, so that's what I'm going to be projecting onto my normal to my tangent line. Okay, so it's going to go like this. 0 minus 3.76 dot product with our U, 0.841 all over 0.841 dot 0.841 times 0.84 comma 1. I'm running out of space. Okay, so remember our dot products. Okay, how we do that. So 0 times 0.84 plus minus 3.76 times 1, right? All over 0.84 times 0.84 plus 1 times 1. Okay, so 0, this is going to become minus 3.76 all over, I think this was 1.7056. I'm showing you all the math. Okay, so I multiplied this out and I put it in together. So this is going to give me minus 2.205 times 0.84 comma 1. Remember, this whole projection bit right here just gives me a scalar. It's a number that I use to scalar multiply my vector that I'm projecting onto. So my end result, my projection of V onto U is going to be, once I multiply this through, I'm going to get minus 1.85 minus 2.205. That's my projection vector. right? It's a lot of work, but we're doing good. We're keeping up. We're going to use that to help us figure out what's the vector reflection or reflection vector. We need that because we need to know, are we going to make it out of this well or not? Wait a sec, I need more paper. Okay, so now, all right, so we need, we're going to call it the incident. This is reflection, right? Incident velocity, right? After impact, which is during our reflection. Okay, so the particle drops down, hits the well, and bounces off. So it has a velocity as it goes, right? So I need to know what's going on. So my incident vector, W, equals V minus 2 times our projection, right? So this is our incident velocity. So this is our incoming velocity, 0 minus 3.76 minus 2 times our projection vector that we just figured out, minus 1.85, 2.205. Okay, multiply through by 2, and then I add all these up. So I'm going to get 3.7, 0.65. And this is my reflected velocity. So you can kind of think of it as like my new initial velocity, right? So my new initial position is the point of impact. My new initial velocity is this thing here, okay? So this becomes our, let's write that down, different color. So this is our new initial velocity, right? We're going to use that to figure out like where we're headed, right? What's our new position, okay? So we need to recalculate our velocity equation using our new initial velocity values. And what does that change? That's going to change our C1 and C2 on our equation, right? Which is going to change our position, right? So let's do this. So my velocity, remember we integrate our acceleration. The acceleration due to gravity doesn't change. So this becomes 0 dt minus 2 dt, right? So when I go to integrate that, what do I get? I get 0, I get C1, and then I get minus 2t plus C2. So it's similar to, it's like the same thing that we did before, only now, right? I have new initial conditions, so I'm going to get new values for C1 and C2. Okay, so now I can say, right, my V, I'm going to use these values here. So this is going to be equal to 3.7, 0.65 to solve for C1 and C2. Okay, so I'm going to set that equal to, so C1 equals my X, 3.7, minus 2t plus C2 equals 0.65. Okay, which means that this is like at time t equals 0 now, right? So this becomes minus 2 times 0 plus C2 equals 0.65. So then C2 equals 0.65. So my new velocity equation is equal to C1, 3.7 minus 2 plus 0.65. I'm going to use this to integrate it to get my new position. You can see how we have an algorithm, right? Where I can keep calling and call and say, the parameter that I'm passing in is my initial position or my initial velocity. What is my equation I'm going to get back, right? So at the beginning, our initial velocity was 0 because we held it and we dropped it, right? And then now our initial velocity, because we're starting over again from the point of impact. So my new initial position is that point of impact, right? And my initial velocity is Like how fast was I going when I bounced off? So this is what we're recalculating. But you can think about it in terms of compartmentalizing, right? If I pass in my initial condition, I'm going to get back an equation for velocity or position, okay? All right, so let's do this. Position after impact, right? So I have to recalculate my position equation. X of t equals, I'm going to integrate my velocity, which means I'm going to integrate 3.7 dt. Integrate minus 2t plus 0.65 dt. Okay. And now what do I get? So my position is going to be 3.7t plus c1, comma. I'm going to go like, remember we integrated minus 2t, I'm going to get minus t squared plus 0.65t plus c2, right? That's just my power rule stuff. Okay, this I need to set equal to my first position of impact. So that was my new initial position to solve for C1 and C2. So X of 0, right? We're sort of starting the time clock over again. Once we impact, right, then we reset our time. T equals 0, now we're going to keep moving. So X of 0 equals now position of impact. Which is equal to, we said, -1 minus 0.54. We calculated that before, remember? So let's do that. So I'm going to use that to solve for C1 and C2. All right, so let's set that equal. So it's going to be -1 minus 0.54 equals my position equation, 3.7t plus C1 minus t squared plus 0.65t plus C2. So this is at t equals 0. So I'm going to go -1, set the x equal to the x. -1 equals 3.7 times 0 plus C1, which is going to make C1 equal to -1. I'm going to go y minus 0.54 equal to my y minus, but it's at, we're resetting our time, t equals 0, plus 0.65 times 0 plus C2. So now C2 equals minus 0.54. Okay, so that's going to give us a new position equation. So X of t equals, right, let's put it all together. 3.7t minus 1, right? And I'm going to go minus t squared plus 0.65t minus 0.54. So that's our new position equation. Okay. You guys with me so far? It's a lot of work, right? But it's okay because we're doing the same algorithm over and over again, right? You can see this is the same repeated thing that we did when we started off at -1, 3, and then we dropped it down, we hit the well. We found out the time when it impacted, right? So we're going to do the same thing. Now we're going to find, we've started the clock again with a new initial position. We have a new initial velocity. And we're going to see, given this new trajectory, is it going to intersect our minus cosine well or not? Okay. So now we're going to use this. So we're repeating the same algorithm. We're going to see if it intersects the our well. New trajectory, which is our reflection, will impact the well. So if it hits the well, then it stays in it, right? If it doesn't hit the well, then we've been able to bounce out of it. Okay, so now what we need to do. So, right, remember, we're like this. We've got our well. We've dropped down and we're bouncing. So now what we need to do is we need to be able to figure out, right, we're headed this way. So now what we need to do is, are we going to hit the well or not, right? So what I'm going to do is I'm going to take a look at the y coordinate. of our parameter. Not the least of which because my cosine well is y equals cosine of x, right? So I'm going to look at the y according to my parameter, and I'm going to see if it is within the bounds of the well, right? Which is y equals minus the cosine of x. Okay, so let's do that. So, so what I need to do is I'm going to calculate y coordinate when x is equal to positive or negative pi over 2. This is our edge of the well. Okay, this was pi over 2. That was given at the very beginning, right? And see what happens. Okay, so I'm going to take my y coordinate. So let's remember our position function. So let me get out my position function here. So the position function that we just calculated, this is, right, this is our reflected, our position function that we just calculated. Let me write that down again here. So my x of t, to remember, is 3.75 t minus 1 minus t squared plus 0.65 t minus 0.54. Okay, so what I'm going to do is I actually have to find the t at which I'm going to use my, I'm going to play both of these off each other. I'm going to use this part to solve for t. So I'm going to use 3.75 t minus 1 equals pi over 2. It's headed this direction, so pi over 2, right? So I'm going to use this to solve for t. And when I find that t, I'm going to plug it into the y and see if that's within the bounds. Okay, so I'm going to use this part here. So I'm going to go 3.75 t minus 1 equals pi over 2. So what I'm going to do is I'm going to add 1. So I'm going to get 3.75 t equals pi over 2 plus 1. That's like roughly, I'm going to round up 2.57. Okay, so I did it in my calculator. Pi over 2, I use the pi button, divided by 2, plus 1, I get 2.57. I'm going to divide by 3.75. I'm going to get t equals 0.6855. So this is the time when we have the next impact. It's either going to hit the well or it's not. So time when next potential impact with well will occur. Okay, so that's the time when it's going to happen. So now we're going to use this t to plug it into the y and see, are we within our y range? Like if I get a y coordinate, is the y coordinate negative? If it's negative, that means I'm still within the bounds of my well. If the y is positive, that means, yay, I made it out of the well. All right, so I'm going to plug this into, my coordinate, right? And then compare it with our values with y values given by well equation. Okay, so let's plug this in. So I've got t equals 0.6855. I'm going to plug it into here. So minus t squared plus 0.65 t minus 0.54. This is equal to y, my y coordinate of my position, right? So minus 0.6855 squared plus 0.65 times 0.6855 minus 0.54. Okay, I just plugged it into my t here. And what I get was equal to y is equal to minus 0.563. Oops. Let's take a look at our graph. Right, so here's, oops, you can't see what I'm doing, pi over 2 minus pi over 2. Remember our well, here's minus 1. Our well goes like this. And it's 0 otherwise, right? So we came right about here, and then we bounced, right? But when we bounced, okay, what's happening is, right, this is my y-axis. This is my x-axis. So all of these values here, my y values are negative. Are negative, right? Because it's below the x-axis. Now let's pretend like if this was shifted up a little bit and I dropped it, then what I'd have to do is I'd have to compare and see if this was in the range of my function. So this right here, right? This value is within range of y equals minus the cosine of x. Oops, which means that our particle didn't bounce out of the well. Therefore, particle does not bounce out of well. If the y value that we got after plugging in, right, the y value that we got was not within the range of that value, if it was positive, we could see it because this whole thing takes place where y is negative. Then we go, yay, it bounced out. So what's happening, right? So it drops down, hits here, and then it bounces off and it's going to go right to there. And then now what's going to happen, right? So this is our impact. This is our first impact. This is our reflection. This is our drop, particle drop. Drops down, reflects, and it's going to hit somewhere around here. And then it's probably going to bounce, bounce, bounce. It's going to basically wobble until it, you know, kind of settles probably somewhere close to the bottom of the well, okay? If it had landed out, like if our gravity was a little different or if our initial condition was different, right? So it picked up maybe more velocity as it landed. If our positions or our gravity were a little bit different, then maybe it would bounce out of the well and we could do something different. But now what's going to happen is it's going to hit here and then it's going to reflect and it's going to reflect, it's going to reflect. It's going to kind of basically end up around there after a few iterations, okay? But this is how we're using a lot of the stuff that we've done. We're talking about intersections, right? I'm intersecting a line and a function, right? I'm doing a reflection. I need my derivatives to come up with the tangent line. Like if I'm going to do this again, right? Imagine I'm going to do this again. I'm going to come up with my tangent line. I'm going to take the slope, right? I kind of already have an equation for it. I'm going to take the slope at this point of impact, right? I'm going to use that slope to calculate out the normal. I'm going to project onto that and reflect it, and it's going to give me the direction of the reflection, okay? So you can see how we're going to do the same algorithms over and over again until maybe we stop. Maybe we say we're going to iterate 5 times if we're inside the well, or we're going to iterate until our y value is, you know, maybe the difference in values aren't changing so much. You're going to set up some kind of criteria so that you don't have an infinite loop where it's constantly calculating this, okay? Unless it makes it out and then it goes on and it does something else, okay? So this is like a sand trap, like you're stuck here now. You need some help to get out, okay? Phew, long example, but it's neat. It pulls together a lot of things that we've been talking about so far, okay? And I will scan this in and I will post it on our Canvas page later today. Okay, guys? Good example. All right. Okay, so I'll put that up there. So that's it for chapter 3.2. And what I'd like to do is I'm just going to do a couple examples from our classwork page just so you can see. And please, like I said, don't do all the examples. We're just trying to, get an idea, of things. So let me get this straight here. We're just trying to get an idea of things. Can you do the integrals? All right. So I'm just going to work through, just a few of these here. Okay, power rule. Okay. I'll do some examples on the back of the page, and then we can call it a day. This one here. So 2/5 plus 1. 1 is 5/5, so 2/5 plus 5/5. And when I want to divide by a fraction, it's like multiplying by its reciprocal. So this becomes right, the 7s cancel. Okay, I'll do this one here. I converted this to a fraction. A root, this is the cube root. A root means a fractional exponent. So if this was just the cube root of x, that would be x to the 1/3. But since I have an x squared, I'm going to multiply that 2 times the 1/3. So I get x to the 2/3 is what that means. So it's minus 5/3 times 2/3 plus 1. 2/3 plus 1 says 3/3. So 2/3 plus 3/3 is 5/3. Right, I'm going to divide by a fraction, which means multiplying by its reciprocal. Which I can say is going to be minus 1 all over. That's a cube root of x to the 5th plus c. Or I could leave it like this. Either way, they're the same thing. Okay, so just a handful of problems. I did probably more than you need to do just to show you what things look like. Okay, guys? All right, I'm going to end here, and I hope you guys will have a great day. Bye.